When most people talk about large language models, it's easy to come away with the impression that the model is just a transformer. After all, self-attention is the idea that gets the most attention, and for good reason. It is the breakthrough that made modern language models possible. But if we zoom out for a moment, the transformer is only one stage in a much larger pipeline. Between raw text entering the system and predictions coming out to the other end, information passes through a surprisingly long sequence of transformations. When we study these transformations independently, it's easy to lose sight of how they fit together. While I was implementing a transformer from scratch for the first time, I also happened to be spending an unreasonable amount of time playing Satisfactory. If you haven't seen it, it's a game about designing automated factories. Raw materials enter at one end, travel along conveyor belts, and pass through a sequence of machines, each performing one simple transformation. Connect enough of them together, and you'll get a production line capable of building remarkably sophisticated things. After enough time switching between my code and those conveyor belts, I noticed that they weren't all that different. In a language model, raw text enters at one end, it passes through a tokenizer, gets turned into vectors, picks up positional information, moves through the transformer, and then comes out the other side as a prediction. Every machine takes in whatever the previous one produced, performs one specific transformation, and passes the result downstream. That's the mental model we'll be using throughout the video. We'll walk the factory one machine at a time, following the data from stage to stage, building intuition for the whole pipeline before worrying about the mathematics inside any single machine. Every factory needs a source of raw material. Ours is a dataset called Wikitext2. Just a bunch of Wikipedia articles, raw text, nothing else. And that's a problem, because text isn't something our model can work with. Every machine in this factory operates on numbers, so before anything useful can happen downstream, we need to convert English into a numerical representation. But not just any numerical representation. Think about what we need it to do. It has to hold some notion of what a word means and express relationships between words. Like, a king and queen are related in a way that king and bicycle aren't. A single number can't do that. A number is a point on a line, and a line doesn't give us room for that kind of a structure. But a vector might. A vector is a point in space, and with enough dimensions, space is roomy. Similar things can sit close together, unrelated things can sit far apart. Suddenly, we have somewhere to put meaning. So, vectors are the destination. The question is, how do we get there? And for that, we need to step into the preprocessing building. So, when we look at the preprocessing building, the first mission we see inside it is the tokenizer. The tokenizer, as the name suggests, tokenizes the language. The purpose of tokenization is to break language down into smaller reusable building blocks and assign each one a unique ID. These building blocks can then be combined to represent different sentences, paragraphs, code, etc. At first, it might seem reasonable to assign one token ID to every word, but there's a problem with that approach. Consider these two words, eat and eating. Should they really receive two completely different token IDs? If so, then we will need separate token IDs for play and playing, read and reading, walk and walking, and so on, making the relationship between these words much harder for the model to generalize, as it perceives each token as a different word and not understanding the pattern. Instead, we allow the tokenizer to reuse smaller pieces across many different words. For example, it might split playing into play and ing, allowing the same ing token to be reused in words like reading, walking, and many others, reinforcing the pattern into the model's vocabulary. After processing the entire dataset, the tokenizer produces a dictionary that maps every learned token to a unique integer ID. That would make the sentences look like this. Now, let's move on to the second mission in the preprocessing building, called the batcher. If we were to process only one sequence at a time, we'd be wasting a lot of compute. Instead, We process multiple sequences simultaneously. This is called batching. We can think of it as arranging multiple tokenized sequences into a nice matrix. One way to construct this matrix is by padding shorter sequences with zeros so that every row has the same length. But if you do this to every single sentence in the dataset, we notice that almost half the sentences will now be filled with zeros. This wastes compute since the model ends up processing a large number of zeros. So in practice, we use something called pack chunking. Instead of padding every sequence individually, we concatenate multiple sequences together and then split them into fixed length chunks based on the model's context length. For example, if our context length is 7, each row in the matrix will contain exactly 7 token IDs. Since the total number of tokens is usually not an exact multiple of the context length, only the final chunk will contain some padding. To indicate where one sequence ends and another begins, we can insert a special EOS token between them. This allows the model to recognize sequence boundaries. For the sake of demonstration, we'll simply use this basic pack chunk matrix of token IDs. Advanced methods include sentence masking, etc. Now, when you apply this to all sentences with a context length of 16 and a batch size of 4, we can clearly see that every sentence is packed with tokens and we are maximizing our compute efficiency. Now, we enter the model building. This is the main building of this factory. Everything in this building is learned, meaning from here on, every machine has settings that get adjusted as the model trains. The first machine in this building is the embedding machine. The embedding machine is a lookup table where every token ID has a vector map to it. Nothing about these vectors is decided. At the start of training, they are pretty random. They carry no meaning at all. But as the model trains and the loss gets minimized, every vector gets nudged over and over again until the arrangement starts to reflect something real about the language, where related tokens end up near each other and unrelated ones far apart. As of now, we've packaged the data into matrices of token IDs with dimensions b, l. Now, replacing these token IDs with their equivalent vectors from the embedding table transforms our b, l matrix into a tensor of dimensions b, l, e, where e is the embedding dimension or the dimensions of the space from which we choose our embedding vectors from. Now we have packaged everything into a nice tensor, but we have another problem. In our mathematical representation, there's nothing to encode the positional information of tokens. Currently, there's no way to differentiate between the cat sat on a mat and the mat sat on a cat, because the tokens are matrix multiplied at once and not processed sequentially. So before this tensor moves any further, every token needs to carry not just what it is, but also where in the sequence it is. A naive way to include positional information would be to append the index of each token in a sentence to the end of the vector, like adding an extra dimension to store the position. But that breaks down fast. Our embedding values are sampled from a normal distribution, so the range for a two-dimensional embedding looks roughly like a circle centered at 0 with a radius of 1. When we add another dimension with integer positioning, the more tokens we have in a sentence, the more embeddings rely purely on position, without accounting for the meaning acquired in the previous range. By the time you're a few hundred tokens in, the extra dimension is so large it drowns out everything the embedding was carrying, and it keeps growing with no upper bound, converting the multidimensional space into a number line without any meaning other than the position. Another way would be to add integer positions to the vector, and that too would not work. You can think and figure out why that's the case. So, we need something that stays bounded no matter how long the sequence gets, and that still lets the model tell positions apart. One thing that's bounded and never stops varying is a wave. Sines and cosines stay between -1 and 1 forever, and with a recognizable pattern. According to the people behind the transformer, the formula for sinusoidal embeddings look like this. Let's see how it works. Take an example sentence. The cat sat on a mat. We then set up the sines and cosines, and then plot the graphs for the token in the first position. We assign the value of sine for even embedding dimensions, and the value of cos for the odd embedding dimensions. Doing that, we get the positional encoding vector for the first token. Then, if we do this to every other token, we see that we get sines and cosines of varying phase for the subsequent tokens. If you have noticed, these values remain same for every single sequence, meaning we can just add the same matrix to all sequences in the batch. Doing so, we get 4 matrices representing all the sequences in a batch of 4. Stacking them together, we get a tensor. This tensor is basically the same as the one we had before, except in this one, tokens are aware of their position. So everything we've built so far has really just been preparation, getting the raw text into a shape the model can actually work with. And what's sitting on the belt now is a tensor that knows what each token is and where it sits in a sequence. But nothing more than that. None of these tokens can look at each other yet. That's what the transformer does, and that's where we'll pick up next time.